Thank you for the introduction, Suri, very warm introduction, and thank you to the organizers for inviting me here. So it's ICTS is also a very nice place to come. I'm always happy to be here. So I will tell you about some combinatorial kind of question born out of algebra, but yeah, there is some combinatorics of Coxeter type in it. So we will introduce the terms and so on. So maybe I should start in the, so this is, I'm reminded of this episode of the Big Bang Theory where Penny wants to understand what Leonard is doing, and so she asks Sheldon to teach her some physics, and Sheldon starts by, what is physics? And let us imagine the scene in ancient Greece 2,000 years ago. So the time was 1930s, the place was Princeton, and a postdoc, Coxeter had just finished his PhD, and he came to Princeton to do a postdoc where Herman Weyl was there. And he came in, apparently, so this is what I read on Wikipedia. So Coxeter came in 1931 for a year or two, then went back to England and to Europe, and then again came back in 1934. And somewhere in between that, of course, Einstein also moved apparently in 1933 to the Institute. But somewhere in between that, Coxeter classified the finite reflection groups the finite real reflection groups. And that is where we start. So we've seen, well, we all know the group of permutations. We've seen the group of signed permutations. These are examples of what are now called finite Coxeter groups. So for Sn+1, we write down these adjacent transpositions and we call them the simple reflections when they act on n+1 dimensional space in this case. And the permutation group is generated, you have a presentation by these generators and these relations. And these are called the braid relations. Either S1, S3 is equal to S3, S1, which is clear. 1, 2, and 3, 4 commute, but 1, 2, and 2, 3 don't commute. So when Si and Si+1, they're adjacent transpositions, then they satisfy this braid relation. And you can, of course, draw some braids and nice pictures, which is why they're called the braid relations. And of course, each Si square is 1, which I will write in blue because we are going to focus on that relation and changing it. Fine. So this is the permutation group. Another example of Coxeter groups is the dihedral group. I2M, so this, I'm keeping n for the number of nodes or simple reflections, and m is going to be the order of SISJ, if you will. So S1, S2 to the m, this is again standard stuff. We all know this from Algebra 1 or something. Right? So for example, the third dihedral group has 6 elements, and these are the 5 elements, and then the 6th one, S1, S2, S1, is the same as S2, S1, S2. That is the unique longest word in the reflection group. And this is, of course, the same as the symmetric group on 3 letters. Okay, so as I said, so this is, Coxeter wrote his paper somewhere in there, and it got published in 1934. This is the famous paper of Coxeter, and it ends with a table of irreducible finite groups generated by reflections. And this is the table in that paper. And I just checked on Wikipedia, again, just for fun, and the Coxeter type, this bracket notation, these orders and everything, it's the same table there as in this original work by Coxeter. These are the Coxeter groups, the finite ones. Okay. So every finite Coxeter group then is, so maybe I should draw one of these just for fun. And then we will come to the thing. Fine. So let me draw this Coxeter group for fun. I'll draw it maybe here. This is the same I3, the symmetric group or dihedral group. So this is, I'll call it the empty word. Then this is S1, S2. Then I'm always multiplying. So if you want, you can write on S1 and S2. And this is S2, S1. This is S1, S2. I'm always multiplying from the left. And then this is W0, which is on the one hand, it is S1, S2, S1. On the other hand, it is S2, S1, S2. Okay. Fine. So multiplying by 2, multiplying by 1, multiplying by 2. I think this is the way I wanted to do it. Oops, I seem. That's clearly, I don't know how to alternate. Fine. So, okay, so this is the Coxeter group, and then no matter which, this is the braid relation. Okay, fine. Okay, so now every finite Coxeter group is given by some data. There's a finite set of generators. There's an integer matrix with positive entries. The entries can be infinite. And then now you have the relations. For off-diagonal entries of this matrix, you get the braid relations. And the diagonal entries are always 2, and that's the Coxeter relation, Si square equals 1. Fine, so this is the usual picture we have. Associated to W now, I'm going to go from groups to group algebras because it's really in associative algebras that this talk is based. And so is this group algebra and I don't even need to work over a field. I can work over any unital commutative ring. Then it's a free module. It's a free module, and this is the rank. So I will keep saying dimension or rank, but it's just the fact that it's a free module, and that is what I mean by dimension or rank. Fine. There do exist other algebras related to W, of course, through this kind of thing with the same dimension. And these are, which are related in the sense that there's a precise way to deform one set into another kind of thing. So, so given a Coxeter system, like this given a set of indices or simple generators and such a matrix, first of all, we define the free associative algebra. That's basically like the tensor algebra. So instead of saying SI for this little s, I'll use capital TI for the associative algebra picture. And the corresponding monoid algebra, like the braid monoid algebra, is the following algebra. Quotient this tensor algebra by the set of words TI, so where the length on either side is exactly the MIJ. Right? So this is the braid, like the braid group thing. So and then here is Artin's paper on braid groups. So actually this is interesting. He says that a theory of braids was leading to a classification was given in some paper of mine. Most of those proofs are entirely intuitive, and that of the main theorem is not even convincing. But it is possible to correct the proofs, and this is my paper here. And the difficulty that one encounters, blah, blah, blah. So I think, and this has led me, I think the spelling of lead is not correct, to abandon projections altogether. And so I think in this paper, he completely avoids any diagrams. Like at the end, there are a few diagrams, but he says, I'm going to not do intuitive stuff, so all calculations, no diagrams. And later on, he has a few, but not very few. Okay, fine. So, but now you have this braid monoid, so you have only quotiented by the braid relations. Now we need to quotient by the extra relations. And these are called, so if you read Humphrey's book on Coxeter groups, the very last chapter starts with defining this in slightly greater generality, but the generic Hecke algebra is this one. And there are special cases. So for example, if I take A equal to 0 and B equal to 1, then that's just the group algebra, because Ti square equals 1, that's the simple reflection, square to 1. But more generally, you can take this quadratic relation and you can specialize to some Q values and get the usual Iwahori-Hecke algebra, which is of course very prominent in representation theory. So do I want to write this down? Maybe I'll write down the monoid. Yeah, I'll write down the braid monoid for fun. So if you have this is a Coxeter matrix. This is my ground field or ring. So this is the tensor algebra. Quotiented by the or do I call them TSTT or something? So this is the two-sided ideal. Okay, fine. Okay, great. So now so the fact is that once you do this quotienting, every such algebra, generic Hecke algebra, has a word basis, and the word basis is exactly the set of words like in the usual Coxeter group. So if you have if you can write a reduced expression for one of these words in the Coxeter group, then the exact same order of multiplying the generators would give you the expression for this word. So these are TWs are reduced expressions in the TIs, exactly the same as the S or the Ws in the Weil group are reduced expressions in the SIs. And the dimension is exactly the size of W. So there are three special cases which are interesting from the viewpoint of various things. At least two things that I know of are combinatorics, of course, because there's some, and deformation theory, which is actually how I came into came to explore this question. One is, of course, the group algebra, that's fine. And deformations of this are exactly the Hecke algebras. So for example, if you take Q goes to 1, then the relations go to the relations in the group algebra. That's in a very informal sense what I mean by deformations. There is the zero Hecke algebra, which at least one of the names or maybe more of them should be familiar to you in the audience, has been studied from combinatorial perspective and bubble sort and various things. And the last one, which is the subject of this talk, Nil-Coxeter algebra. So now Ti square is 0. So maybe I'll just write down the Nil-Coxeter algebra. So I made a list of what I should write down. So write down the Nil-Coxeter algebra. I'll call it Nil-Coxeter M. Okay, this is, as you can see, I'm leaving some space here, which will be relevant later. Maybe I'll just quotient the braid itself. No, maybe fine, I'll say this here, fine. Quotiented by two things. One is the braids. And then the Coxeter relations. Coxeter relations, Ti square equals 0. So these are for all I naught equals j. These are for all I. Again, the two-sided ideal. And again, this is one example of generic Hecke algebras. So therefore, the dimension is still W. And the basis is still the basis of worlds. And these guys occur naturally as differential operators, divided difference operators in Schubert calculus. So for example, in type A, this would be the operator. So you take a function of n plus 1 variables. Remember the type A while group was Sn plus 1 in my convention. And now you take just the usual f minus the f where the ith simple reflection has been applied to the variables. Now by whatever, some theorem on polynomials, this is divisible as polynomials by that denominator, so you divide it. You can check that if you do this twice, then you get 0, and the reason you get 0 is because already the numerator here is alternating in xi and xi plus 1. So when you divide by this, it's symmetric in xi and xi plus 1. Now when you take that symmetric function here and you switch this basis here, it's still the same function being symmetric. So the numerator becomes 0, and so Ti square acts by 0. So certainly it's easy to see that these relations hold. It may be less easy to see that these relations hold, but probably there is some clever combinatorial trick that makes it clear that the braid relations also hold on the Ti's. So yeah. Okay, so that's one place where the Nil-Coxeter algebras occur naturally. Yes. Oh, I'm so sorry, yes. Clearly I've forgotten about n plus 1. That should be n plus 1. Thank you, Joel. Yes. Very good, yes. Since I made a big deal of it, yes, I should not have a typo. Okay, so now the dihedral group has these elements, as we said. Clearly I forgot the element 1, I'm sorry. I don't know why, but they increase in length all the way to this unique longest element, and correspondingly, just to remind you that the Nil-Coxeter algebra has the same basis, and again I forgot the element 1, sorry. It's a unital algebra, so it has a scalar, the unit. Yeah, so again, these guys increase, and again, all the way to the longest element, which corresponds to W naught, but because it's in these generators in the algebra, I will call it TW naught. W naught will refer to the group element upstairs here. The corresponding thing would be T1, T2, T1, T2, dot, 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 equals T2, T1, T2, T1, dot, 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 that equals TW naught. So now we come to the main player in this talk, the generalized Nil-Coxeter algebras. Oh, okay. This is silly of me. Fine, I will move this. The whole point was not to do this. So, the symmetric group 2 inches to the right. This was what? I'll call it the empty word because I want to call it the empty word. S1, S2, I'm stopping writing these things. Then I put left multiply, so I left multiply. because now I don't want to use S, I will be using T's. So let me not write the S here. Okay, so generalized Nil-Coxeter algebra. Now, where does this come from? Here is one place where these generalized things come from. The idea was, remember that we had SI square equals 1. So what happens if I do SI cube equals 1 or SI fifth equals 1? And this is not my question, it is Coxeter's question. So he studied what he called the generalized Coxeter group, defined as the quotient of this type A Artin-Braid monoid, the usual that BM in type A, by this relation now. And one should note that, of course, in real groups, reflections have order 2. It's really complex groups where reflections can have higher order, so this might remind you of complex groups. I have a slide on complex groups later. Okay, so WAND is a finite group if and only if, this is his theorem, N and D satisfy this condition. And then this is actually the dimension of the size of this group, and that will give you that the fact that that's an integer is a corollary. This is in type A, but you can again try to do something similar in other types, and this was done by Coster a few years later. There is some classification. You can look at the paper of Coster for the classification. Fine. So in Coxeter's construction, all the SI are conjugate, right? Why are they conjugate? That's not hard to see. I won't cross this line. If you have something like say S1, S2, S1, S2, S1, S2, then that's the same as saying that S1, S2, S1, and then S1, S2 inverse is S2. Which means that instead of saying, see here I could have taken S1 to the 3 is 1 and S2 to the 4 is 1. But that doesn't quite work because they are conjugate, so their orders have to be the same. So then you would have to take the GCD of 3 and 4. So really you might as well just take the common GCD of the individual powers, and that's really what matters. So SI power D is 1. And this is what Coxeter worked out. These are the only ones when it's finite. Or well, these are the ones, maybe not only. But now in the Nil-Coxeter case, there is no such conjugacy. There are no group elements acting among the generators. So I can choose individual powers to be independent of each other. So that's what I defined to be the principal player. Question? Sorry. No, that's okay. Feel free to ask me questions. I thought there was a question. So the number of generators is fixed at 2 or? No, anything. So this is over any Coxeter system. Right? So define. Cardinality of I, right. It's always a finite set, but I don't care how big. So now, given a Coxeter data. Since I'm going to ask for the dimension to be finite, of course, none of them are infinite anyways, so it won't matter. Yeah. So the question is again to understand which of these are finite dimensional, just following Coxeter. Right? So define the generalized Nil-Coxeter algebra to be the same kind of thing here, but now I can change this to be a tuple D. This is why I had left the space here, and the Coxeter type relations are changed to Ti to the Di equals 0. Okay? So that's the protagonist of this talk. Okay, I don't touch the braid relations. Those are sort of sacrosanct. You don't touch them. Maybe because Coxeter didn't touch them. I don't know. Anyway, so question like Coxeter, following Coxeter, for which matrices and integer tuples is this algebra finite dimensional? Does it have a word basis? Nice. Does it have a length function, word basis? You can ask all these questions. Fine. And so clearly, of course, if you take all the DIs to be 2 and W to be a Coxeter group of finite size, then that works. The question is, are there any others? And there's an obvious answer, yes, there is at least one other algebra, which is the very simple one. Okay, well, I wrote it down here. Oops. Okay, I'll tell you the simple one afterwards, clearly. There are some others, so now let me tell you, spend a few minutes on some motivations. So one was, of course, just following Coxeter's question, but that actually wasn't the reason why I studied these algebras first. That was to do with the third motivation, which is not yet mentioned. I'm sort of going in reverse chronological order, but here is one other point that you should note. So if you have studied something, the theory of Hopf algebras, maybe either in combinatorics or otherwise, or bi-algebras, then these algebras possess a coproduct. So Why? Because if you look at this relation, so coproduct is simply something that is a map from an algebra A to A tensor A, which is multiplicative, which is an algebra map. Right? So you extend by linearity on some basis. So these generalized algebras here, Nil-Coxeter algebras, as I said, they also have a word basis. The same word basis, TW, W and W. Right? Where you write a reduced expression for TW, you multiply the simple generators in that order, you get these guys. And because of the braid relations, any two reduced expressions give the same answer here because of the braid relations holding here as well. So we have a word basis. So you can define because this is supposed to be an algebra map. If it's just literally group-like, if the TIs are group-like elements here, then TW will also be group-like. This by multiplicativity will be TW tensor. That's a basis. So now you have extend by linearity. This is an algebra map. So delta is an algebra map. This is a coproduct, genuine coproduct, if you will, on such algebras, generalized Nil-Coxeter algebras. The only thing is in Hopf algebra theory, the reason, so why are coproducts important, right? In say physics or representation theory. Coproducts are important because they allow you to take tensor products of representations. Another thing you want to nicely hold in the category of representations that you are studying is you should have a unit object, the one-dimensional representation. That is what is given by a co-unit. Now it turns out that, so if you have an algebra with a coproduct and a co-unit, then you would get something called a bi-algebra. The point is this, because the TIs are nilpotent, you cannot have a co-unit structure on this algebra compatible with a coproduct. You cannot, one can prove this. So it's not that it may or may not, it doesn't exist. Similarly, an antipode would be nice to take duals, but again, if the co-unit itself isn't there, then there's no point of antipode. The defining axiom involves the co-unit. So the point is this is an algebra map, but cannot have a co-unit and hence not an antipode. So these are not even bi-algebras, and hence their modules don't form a monoidal category. So remember a monoid from algebra 1 is a set with associative operation, blah, 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 and a unit element. Without the unit element, it's called a semigroup. So these don't form a monoidal category, but one can still do the same Tanakian business that one does to recover somehow yeah, and you get what one calls as semigroup categories. And if you have seen, I think Ettingoff and Schiffman's book on quantum groups, then this is referred to. I think it's there. Yes, but the co-unit satisfies some axiom where you get 1. Epsilon of delta of mu is 1 or something like that. And you don't get 1. Yeah. This is a unital algebra with a coproduct, which is an algebra map. So the co-unit should be something so that I get a bi-algebra. And I don't get a bi-algebra because of the compatibility failure. Right. Yeah, the co-unit is an algebra map, but it fails to be compatible to give a bi-algebra. Right. And the third, so this is the actual reason why I came into this problem, which is because the point is, I did my PhD at Chicago, and my advisor Victor Ginsburg and Pavel Ettingoff were studying these things called symplectic reflection algebras and Cherednik algebras, and you have something like a Weil group acting on the polynomial ring. I'll just call it A2n or something, AN. Just a polynomial ring, or maybe a UG, a Lie algebra acting on some polynomial ring. And maybe I'll call it vector space. V is a vector space. And so they were looking at, they started by looking at just the fact that these things have PBW theorems. You can write down some nice basis of these smash product algebras. And the point was that in both of these cases, the first factor here is a Hopf algebra. And that gets used, and this was then later made more systematic by this program of Anne Shepler and Sarah Witherspoon. At least one or two papers with Chelsea Walton, where they again look at, say, Hopf algebras acting on some polynomial algebras or Koszul algebras and so on. And they use the Hopf algebra properties to derive the PBW. When does a PBW basis exist? In this case, the Nil-Coxeter algebra is not a Hopf algebra, it just has a coproduct, and what I showed was that coproduct is enough. You don't need antipode or co-unit to do all this stuff. So that was why, these are some extra motivations for studying, why I was studying this question. But then I got interested in the combinatorics itself, which algebras are finite dimensional. So these don't care about finite dimensionality. This question does. So, but now that question, so these two were done and then this question remained. And so what is known? Okay, so back to the question, classify these finite dimensional ones outside of the usual Nil-Coxeter algebras. Those are known, so what are the rest of them? So as I said, there is at least one obvious finite dimensional one, which is the simplest case. You take, literally you take one vertex and I take any power d. So what is the Nil-Coxeter algebra corresponding to this? Let's call this vertex 1, so T1. There are no braid relations because there are no vertices. The only one is the Coxeter relation, which is T1. This is clearly d-dimensional, it's finite. That's clear. A not so obvious positive answer is two-dimensional, and this is why I needed to keep space and I forgot. So the point is, you can see the picture here, but the idea is this: I take T1 to have degree 2, nilpotence degree 2, only T2 to have higher nilpotence degree. Right? So I've multiplied, so this is like T5, which is the word 1, and then this is T2. I can multiply again by 2, I get T2 square. I can multiply by 2, I get T2 cube, and then till 2 to the d minus 1, I guess. Yeah, so d prime is d minus 1, right? And at each point, I can then multiply by T1, so I would get T1 times T2 square, or T1 times T2 cube. But if I multiply this by T1, then T1 square is 0, so I would get 0, so I don't get a basis element. I mean, one has to prove these are independent, but believe me that they are. If I multiply by T2, what happens? Then I have T2, T1, T2 square. But that's a braid relation. So I can write down T1, T2, T1. Am I doing something wrong? Let's see. I forgot a 1 here, sure. Otherwise fine. Now look, now this is a braid relation. So I get T1 times T1, T2, T1. Okay, fine. Here's a T1 squared, that's 0. So I can't do that. So therefore, T2 or T1, neither of them multiplies to give a non-zero word. And similarly, and then on the other side, you similarly have, from this side, you would get, I multiply T2, so then here I would multiply T2 again, so T2 square T1, and then, and I go up again, right? So T1, T2 square T1, and you get the idea. That's the picture here. So these are sort of all the possible combinations you can do to not get zero words becoming zero because of the braid relations. The claim is that these are all exactly linearly independent and form a basis. That requires some proving, but it's a nice picture. So now, of course, it cannot just be extended to n equals 2, but to every single n. So here is a new rank 1, type A finite dimensional family with exactly one vertex of higher nilpotence degree. Everything else is degree 2. Only one vertex. So for every n bigger equals 1, then n equals 1 was here, and every d bigger equals 2, the type A generalized Nil-Coxeter algebra with only one extremal vertex of higher degree is finite dimensional or finite rank, whatever. And the basis, one can write down an explicit basis. So the proof of this thing involves, I knew sort of 1 or 2 different ways to prove something has a particular basis. I didn't just want the dimension, I wanted a basis. And then this is this thing, sorry. Inside the generalized Nil-Coxeter algebra of type B. I will get to that. Nice question, thank you. It's a very natural question. Does something like this sit inside a bigger generalized Nil-Coxeter algebra of a different type, maybe with some different parameter of nilpotence degree or something? Okay. So yeah, so the proof involves literally writing down, like, here is the vector space, which is the same thing, and here is the algebra, which is the same thing, and one acts on the other. But label them by different things and say that one is the regular representation, one is the algebra, and define the relations the way you would, and check that everything is compatible. And it worked. So one can therefore, we could compute its rank, This is this, and this follows from the word basis itself. So the idea is there's a separate set of bases. So first of all, you have the words not involving the highest, the higher nilpotency generator. Just words in this guy. That part is just the usual Nil-Coxeter algebra with one size less, one less vertex. So that's just n factorial many here. Remember, there are n plus 1 factorial is what I'm generalizing. Right? So n factorial from the one less generator part. Okay, and then the remaining guys have at least one power of the last nilpotent generator. That power cannot be d, so it has to be at most d minus 1. It at least is 1. And there's at least one power of Tn. Then you start applying the lower indices one after the other and stop at some point, wherever you want to stop. But apply them contiguously, consecutively. Turns out these are all, these form a word basis over any commutative ground ring. Then you can write down the unique longest word, which is when k equals the biggest thing and m equals the smallest thing, m equals 1. Then you can write down left or right primitive words, which are words which get killed when you multiply on the left by any generator or on the right by any generator. There are more than one of these if the nilpotence degree is higher, one for every value of k. The longest word is unique because it's longest. The usual length function extends here, the number of letters you need, that's the same. And here is the Hilbert-Poincare series. I'm just presenting some facts about this algebra. It's a nice algebra. I don't know what the center is and so on. Maybe it's interesting to study this algebra in its own right as an algebra. I was just interested in the combinatorics, so that's the data that I have. Okay, so these are the, there's at least one extra algebra that's finite dimensional. Are there any others? The answer is no. This is literally the only one. So somehow, I don't know why this algebra is so special, but it is. Okay, so the algebra is finite dimensional or finite rank, if and only if either, this is the usual Nil-Coxeter algebra, just all the di's are 2. Or it is the algebra I just wrote down for you. I don't care which vertex is higher nilpotence degree, it's obviously isomorphic. These are the algebras we called NC, Nil-Coxeter of type A. N letters and the last, one of the extremal vertices has nilpotence degree D. And the proof of this is going to use a diagrammatic calculus, which maybe I should, I'll just do it on this side. The point is in the next 17 minutes, I want to get to the open question that there remains. So I'm telling you why, I'm telling you sort of the technique that I'm using. So let me just show you this one. So I won't do this one, but I'll tell you what this stands for. Suppose I have this, so I can look at any Coxeter graph, I have some Coxeter graph, there are some nodes, and then there are some edges between the nodes. There is a label like for the MIJs, you have some I or some J, and then you have DI, and then you have DJ. Okay. If I want to write the DIs and DJs also in the Coxeter matrix, I would call this MII and MJJ. The diagonal entries, and then off diagonals are the thing, and there is some graph here. Fine. So one has to start ruling out things, like there are no cycles. So because all the finite Coxeter graphs don't have any cycles. So there are no cycles here, so you have to rule out cycles and stuff. Let me just use the first picture, the square, to rule out that there are, so claim there don't exist alpha and gamma. These are in I. I'm just using labels that I used in the paper. So there don't exist nodes, alpha and gamma, with DI, which is MII, or D alpha, and D gamma, then gamma gamma, bigger equals 3. I don't have, they don't exist adjacent. There don't exist adjacent nodes with labels bigger, nilpotence degree at least 3. That is for the first one, and that's actually a special case of the second one, which is that there don't exist non-adjacent ones either, connected by alpha, beta 1, beta m minus 1, and gamma. So if there are two nodes, then if they were separated, then write down in linear order alpha, beta 1, beta 2, beta m minus 1, then this picture would help us disprove such a configuration. But let me just do the special case where they are adjacent. I don't need it, that's the second picture, but just to prove it. So proof, define a K module or K vector space, whatever, free K module. Let's say M with basis as drawn. So AR, BR, CR, DR, R bigger equals 1. These are the names of vectors. These are the names of vectors in the module or basis elements. And the relations are as follows. How does this algebra, whatever this algebra is, act on this module? So I have these nodes alpha and gamma. So I have simple generators, T alpha and T gamma. T alpha sends AR to BR. T alpha of AR is BR. The next one is T gamma of BR is CR. Okay, this gamma and R may be confusing. I don't know what to do, sorry. Please forgive. T gamma CR is DR. And T alpha DR, and now you will notice I put a plus over there, is AR plus 1. So the plus means that when I act on this thing, I raise the index by 1. And everything else, T of any other beta, any other node, T beta acting on any of these is 0. T alpha acts on AR, T gamma acting on AR is also 0. T gamma acts, so T alpha acting on BR is 0, T alpha acting on CR is 0. So everything else is 0. And now you can check that my relations here, these relations are satisfied with this action and all others are 0. So for example, if I want to verify the braid relation, so gamma alpha, they are adjacent. So gamma and alpha are connected. So if I act by T gamma and then T alpha here, that is non-zero. But because these are adjacent nodes, the braid relation at least has length 3. It may have more, but it has at least length 3. So I need gamma, alpha, gamma. There is no gamma, so 0. Alpha, gamma, and then again alpha. Technically, I should be backtracking, but you get what I mean. There are no 3 consecutive arrows in the braid relation format, so all braid relations applied to anything gives me 0. Any other node, T beta already gives me 0, so T beta square is 0, or any higher nilpotence degree. As far as T alpha goes, well, I know T alpha cube is 0. I don't care about T alpha square. So I have an alpha square, but that doesn't matter because it's T alpha cube that's 0 or higher. So you can check that this is satisfied. Maybe there's some connection to the rags, you mean? Yeah, I don't know. Yeah. So, and the other point is, the final point to notice is this entire module is generated by one vector. It's a cyclic module. Because you keep going, you can keep circling around. Which means, what does this mean? This means that this, whatever this Nil-Coxeter algebra is, it surjects onto M. And M is finite infinite dimensional because it's just 4 times infinity dimension. This algebra surjects onto it, so it's infinite dimensional. So this is how you rule out the existence of 2 adjacent nodes with nilpotence degrees larger than 2. This is how you rule out the existence of 2 nodes at all with nilpotence degrees larger than 2. And you rule out various cases. So that's how you get rid of these things. Okay, so that's this. There is another motivation which I have 11 minutes, so I will skip, but this comes from complex reflection groups and some freeness conjecture by Brouet, Mallet, and Rouquier. I'll just mention very quickly, what they said was that complex reflection groups also have Hecke algebras. Which of these are finite dimensional? They claim that all Hecke algebras, well, sufficiently generic parameters, Hecke algebras, like generic Q kind of thing over a complex reflection group are still free. with some finite rank. This was proved by Tinkoff in characteristic 0. As far as I know, finite characteristic is not fully settled yet. It's some big conjecture from almost 30 years back. What about our generalized Nil-Coxeter algebras? Do there exist finite dimensional ones over a finite complex group? And do there exist ones which have the same size as, same dimension as the size of the group? And the point was, without the word generalized, this was already, I think, known to be no, because Ivan Marin had written a paper which said that the lack of Nil-Coxeter algebras of this dimension, exactly the same correct dimension, is, well, they are lacking. So it's a striking difference between real and complex reflection groups. For real groups, we have the usual Nil-Coxeter algebras. And he said the word Nil-Coxeter, not usual Hecke algebras. But for complex groups, there were no usual Nil-Coxeter algebras of that correct dimension. And so that was actually another motivation. And what we proved is, forget that dimension, there are no finite dimensional ones if you start with a complex reflection group. Just like even the theorem here was that there are no other finite dimensional ones except for the usual complex groups, the usual Coxeter groups, except this one type A thing. So this type A is special among real and complex reflection groups and all higher nilpotency classes. And you just have one vertex of higher degree. In particular, type Bn or Cn, there are no such ones of any other type. Okay? So to answer that question, there are no finite dimensional ones larger than this of any other type. These are the only ones among real and complex reflection groups. Now, of course, a natural question one has to ask is, where do they occur? Like, do they occur in nature? So, and the most simplest one, right, is this one. And the even simplest one among these is just this. Now, kt mod t square occurs in nature because no differentials of any exact complex square to 0. So you can say, well, that's one place where they occur. The differential is t is the differential. What about this one? Maybe over some finite field of positive characteristic or not, I don't know. So in some sense, can one categorify this algebra? And when I wrote this paper, I was actually visiting New York and I met Khovanov and I categorized. So you have to ask Khovanov. But Khovanov also had a paper about Nil-Coxeter algebras categorizing the Weil algebra. So it was very, he was the person to ask. So I asked him and he sort of got very excited and said, I thought about this when I was younger, but no. So, but it would be nice to have some place where this was categorified, or more generally, these algebras where they naturally occur. Like, you know, when d equals 2, the usual Nil-Coxeter algebras are these divided difference operators. For d equals 3 or 4 or anything else, do they exist? Like, do they occur as some endomorphisms of some ring or some vector space? Not just the regular representation, not the cheap one. Okay, so fine. So this doesn't exist. So finally, you know, what next in the last 7 minutes? What next? Now we come to the second part of the talk. This is joint with a really talented undergraduate at our place, Sutanay Bhattacharya. He is now in San Diego doing his PhD. So now we have made these generators, these relations long enough and killed them. We should kill the braid words that are long enough. That's the only other thing one can do, and that is again done in the literature. So Kenneth Fan defines this Nil-Temperley, well, he didn't call it that, but the quotient of the Hecke algebra. The Temperley-Lieb algebra in, say, simply laced type is the quotient of the Ihahori-Hecke algebra generated by the ideal generated by these terms. So this the braid relation plus lower length words gives you 0. Okay. And of course, these have to be adjacent nodes. So TS, TT is not, they don't commute. So one can do the nil version given a Coxeter group with the same index set and Coxeter matrix. The Nil-Temperley-Lieb algebra is the quotient of that same braid monoid, which is written here again for your reference, by the braid relations, but now I kill them. Relations of length 3, I could do this in type B, and I can say I kill length 4 and higher, or length 5 and higher in type G, I guess, yeah, or dihedral type. The Coxeter relations Ti square equals 0. So I kill these guys because this is the usual nil version, which we will do generalized nil later on. And the braid relations have to be killed. That's the extra part. So of course, TT, TS, TT also gets killed. So both sides get killed. These were also introduced completely differently by Alex Postnikov at MIT. He did not, I think, he never wrote the paper on this. An undergraduate at MIT with Tanya Khovanova wrote a preprint, which I think they didn't publish either. It's on the archive. I think it's called XYX algebra. So like XYX equals 0, that kind of thing. And then they classified which of those were finite dimensional. But essentially, that was the same thing as what Kenneth Fan and Stembridge had sort of done earlier. So let me tell you the answer. So first of all, notice that which way does it go, right? I'm saying these surject onto Nil-Coxeter algebras, right? And then which of these are finite dimensional? Do they surject? Now I'm confused. Anyway, but the answer, I think they do, because there you get more answers here. Right? So this Nil-Temperley-Lieb algebra has finite rank or finite dimension if and only if W is a finite Coxeter group, meaning then you do get those. No. These are surjected onto, sorry. The Nil-Coxeter algebra surject onto them because you further kill these guys. So if the Nil-Coxeter algebra was finite dimensional, these guys are finite dimensional. But if the Nil-Coxeter algebra is infinite dimensional, that doesn't rule out these guys being finite dimensional because you're quotienting something extra. Right, so that's another typo, sorry. So in particular, En, Fn, and Hn, all of these guys have finite dimension, finite rank, for the extra quotienting by killing the braid words. They don't have, without this relation being done, just braid equals braid, that's infinite dimensional. But when braid equals 0 and braid equals 0, then that's finite dimensional for all of these, and these are the only ones. So this was, I think, done by Stembridge and Kenneth Fan for the non-nil version, the usual version. But roughly speaking, I'm saying it's essentially known because of deformation theory, PBW deformation. So it's essentially known. So these are fine. Generalized. In the generalized version, you just have, I don't know why there's extra S, because, well, this slide I made on the way here in the taxi, so sorry. So, not just this one, all subsequent ones as well, probably. So, right? Yes. So, and of course, the nilpotence relation has to be generalized or weakened. Which of these guys with the extra parameter D now are finite dimensional? And the answer is, this is the result of Vitsutane. If these are the algebras on this slide, all of these guys are finite dimensional. That's all of the D's are 2. This is the usual thing where all the squares are 0. The XYX algebras of type 3. So this is the only one which is finite dimensional, which is the same algebra that I gave you, but of course then you have to quotient out the X a little bit more. And in that case, in the first case, this is what Stembridge and Kenneth Fan had already computed. The dimension is the number of fully commutative words. So really, this was classifying the Weil groups or the Coxeter groups, finite or infinite type, with the number of fully commutative elements being finite. That's if and only if, and that's actually the dimension. That's actually a length, a word basis. Okay? In the second case, this becomes more refined than just the earlier type combinatorics. So I think with 2 here, if D was 2, the usual Nil-Temperley-Lieb XYX Postnikov algebra, D minus, all this just vanishes because D equals 2. So all you get is the Catalan number. When D is bigger than 2, one has to do some refining of that calculation, which you have to rule out certain other words. Not rule out, you actually expand, you improve on that, sorry. And so what you get is this extra expression, which is it is what it is. Some Catalan combinatorics going on. Okay, so I think, let me just, before I give you the references, since I have 1 minute and 16 seconds, let me tell you the open question at the end, which was basically the fact that here what I did was I killed off all the words of length 3, because this was simply laced type. But in principle, I need not kill it off. Then I just get my usual generalized Nil-Coxeter algebra for simply laced type. But I could kill words of length 4 in type B, or I could kill words of length 5 in type H, or in type G, or I could kill words of length 4 in type F also, right? So it depends on what length you kill. And for killing words of, so the only case that we haven't solved yet, open question, is for type H. Type H, killing words of length, I'll have to look it up myself, I mean, some of them are solved and some of them are not. When type HN, yeah, killing words of length something. There are a finite set of words that I need to kill, a finite set of lengths, not 6. 6 and above is just the usual Nil-Coxeter because there are no braid words of length 6 in type H. So I don't need to worry, or in any larger type. Killing words of length, which n yield finite dimensional generalized Nil-Temperley-Lieb. That is the open question. That's literally the one case that we haven't been able to work out. And the idea, we are hoping, the idea is we can draw some kind of such diagram. The diagram that I drew here, there is a diagram. The diagrammatic cat and this. We can do some kind of such thing and then hopefully, like maybe just say H5 is infinite dimensional. The moment H5 is infinite dimensional, everything larger is. But even for H5, then you have to draw diagrams where the arrows are labeled by 5 vertices. And it's a mess. I mean, maybe somebody with cleverer mental intuition and cleverer ideas can draw the right electrical wiring diagram and get no contradictions. Therefore, there's an infinite dimensional module. Therefore, the algebra is infinite dimensional. Maybe, but I invite you to try if you want for H5. Okay, that's it. It's just like playing games.
Type page full. What is type page?
Oh, H is this horrible one, right? Huh? H for horrible? No, H is nice. H is I think maybe one more here. H is a non-crystallographic one. So like dihedral. So A through G are crystallographic, Weil groups. H and dihedral are non-crystallographic. So you get like root 5 expressions of root 5 in this. In doing the Euclidean reflection calculations, you get root 5s.
Does it occur in nature?
It's a finite reflection group, so yes. It's a Coxeter group. Of course it occurs in nature. Faithfully, it occurs in nature. Yeah.
Other questions? Yeah.
If you recognize that number, I'll give you dinner. I don't know. I will have to check. This was like, yeah, it makes sense, exactly. Number of words of a given degree, a given length. And I should check, I don't know. So I forgot to mention, so you can also do this for the killing words of length 4 or more in type B, and that's where you get this 1 bar, 2 bar avoiding permutations. And you have connections to various combinatorial quantities, and one of them is such pattern avoiding permutations in type B, one is Catalan. I don't think I'll have to look, I'm sorry. This part is also Sutane, so I will look at the paper and tell you, but it's also 3 years old. Like if you asked me 2 years ago, I would know the answer. Now, yeah, I've been too busy to look at it, but yeah, I'll check. It's a good question. Actually, a bunch of these things are not known. So, I mean, even the type A that we haven't explored. No, it's all open or left to explore. Even Nil-Temperley-Lieb, I think Georgia Benkart and one of her students wrote a paper on the center of this for the usual Nil-Temperley-Lieb. And I'm not even sure they did the whole thing. Maybe they found some central elements. I forget. So, but again, the generalized ones are all sort of, these are finite dimensional algebras, but we don't know it. The only thing I can say, the one thing we did prove, or I proved in this thing, and then we extended it to the Temperley-Lieb cases, are they Frobenius? And the usual Nil-Coxeter algebras are Frobenius, that is well known. This algebra, this one is Frobenius. That is very easy to check. You just define some bilinear form. No other, so if you look at NCA, N and D bigger than, D is bigger equals 3 and N is bigger equals 2. These are not Frobenius. This one, for N equals 1 is Frobenius, for all D, N equals 2 and above is not. If it's not the usual Nil-Coxeter. That's the only one.
Last question. Yeah, last question.
Okay.
Like Bureau representation, is there some such thing which you can?
Nothing explored. Feel free to explore. Yeah, we just looked at the finite dimensionality and word basis kind of. Okay.